This data packet is moving toward a network's core, and it pierces the external perimeter defenses without triggering a single alarm. This diagram shows how standard microservice architectures protect the perimeter. You have an external client, a web application firewall, the public web server, and an internal database. When a malicious packet comes from the outside, it hits the web application firewall and gets rejected. Modern web applications are designed to be interconnected. They routinely fetch external resources, resolving an image URL, pulling in a webhook, or downloading a document based on a link provided by a user. If the application does not strictly validate that user-supplied URL, it exposes a direct vector. An attacker can instruct the application to fetch data from a malicious target. Here, an attacker sends a seemingly safe request to the web server. Once inside, the server pivots, generating an unauthorized request. Originating internally, it bypasses the firewall and strikes the database. This mechanical failure is called Server-Side Request Forgery, or SSRF. While Cross-Site Request Forgery involves compromising a user's browser session, SSRF operates on the backend. It turns the server itself into an attacker's proxy to compromise the surrounding infrastructure. Perimeter defenses like firewalls fail entirely if the internal backend implicitly trusts all requests that originate from its own web servers. This mock REST API post request shows a typical feature, an inventory stock check. The application uses the parameter stock API to pass a URL, telling the server where to fetch the actual data. Normally, the server queries this legitimate internal domain, parses the data it receives, and returns the stock count to the user. Now, an attacker replaces the legitimate URL with a loopback address, targeting a sensitive endpoint, http://localhost/admin. The request leaves the web application process, but immediately loops back into the server's own administrative port. The server processes this modified request by querying its own loopback adapter, specifically the IP address 127.0.0.1. Internal administrative interfaces and debugging tools often lack authentication checks when accessed via localhost. The admin access control node sees that the request is coming from its own internal IP, assumes it is a trusted system administrator, and automatically hands over the data. This mechanical failure exposes a critical architectural flaw. Developers often assume that network topology, the fact that a service is not exposed to the public internet, provides sufficient access control. SSRF weaponizes the server's implicit self-trust, instantly granting external attackers the exact same privileges as a root-level system administrator. Once an attacker compromises the local server, they can use it as a beachhead to map the broader internal network, targeting non-routable private IP addresses on 10. or 192.168 subnets. Looking at this network cluster, the compromised server sits in the center. The attacker uses it to scan these private subnets for unauthenticated internal microservices, like Memcached or Elasticsearch. The private data flows from the node back through the server and out to the external attacker. This threat escalates significantly in modern cloud-native environments like AWS, Google Cloud, or Azure. Cloud providers use the Instance Metadata Service, or IMDS. This is a REST API that provides configuration data, and it is accessible exclusively from the virtual machine itself. Every major cloud provider places this metadata access at a hard-coded reserved IP address, 169.254.169.254. If an attacker can force the web server to send an HTTP GET query to this specific metadata endpoint, the cloud provider will expose the environment's sensitive configuration data. The ultimate payload here is identity. The metadata node generates a JSON packet containing temporary identity and access management credentials, the access key ID, and a secret access key. This packet flows backward through the proxy server into the attacker's hands. This exact mechanism drove massive data exfiltration events like the 2019 Capital One breach, where gigabytes of sensitive financial data were pulled from cloud buckets. Cloud-native SSRF creates a direct pathway for attackers to escalate from a single application layer vulnerability to the administrative control of the entire infrastructure. The standard developer response to SSRF is to implement a simple blacklist. This mock backend logic shows a string matching filter designed to drop any request containing the exact terms localhost or 127.0.0.1. This fails because of alternative IP representations. Attackers can mathematically convert standard IPv4 addresses into integers or octal formats. In this diagram, the attacker inputs the integer representation of localhost, 2130706433. The text-based filter scans the string, finds no match for the word localhost, and gives it a green checkmark. The application's basic filter allows the raw string, but as it enters the backend HTTP client module, the underlying client automatically translates that integer back into 127.0.0.1. The loopback IP is accessed and the attack executes. There is a second common bypass technique, open redirection. In an open redirect attack, the user supplies a seemingly safe whitelisted domain. However, that domain is configured by the attacker to instantly redirect the server to an internal IP. The backend server validates the initial safe domain, but then it blindly follows the subsequent HTTP 302 redirect status code directly to the malicious destination. Even if the server is configured to hide the response data from the attacker, a scenario known as blind SSRF, out-of-band signals like DNS lookups or timing delays can still confirm that the exploit was successful. Defense based on input blacklisting is a failed strategy. Attackers will endlessly exploit the discrepancies between how your validators read a string and how your network clients interpret a destination address. SSRF exists in the gap between intended application logic and actual network trust boundaries. Looking at this split-screen diagram, the primary layer of defense happens at the application layer on the left. Instead of a blacklist, you must use strict allow lists of pre-approved domains. To neutralize parser evasion techniques, the application must validate the fully resolved hostname, not just the raw string provided by the user. You also have to explicitly disable unused URL schemas, blocking local file access or obscure protocols like file : or gopher : You must assume that code-level defenses will eventually contain a flaw. Moving to the right side, the infrastructure layer acts as the failsafe. This means applying least privilege network egress. The application container itself should be restricted from initiating any outbound connections to private internal IP ranges. To protect cloud metadata specifically, you need to upgrade to session-based metadata protocols like AWS IMDS-v2. IMDS-v2 requires a specific cryptographic token to access the metadata endpoint. This neutralizes the blind HTTP GET requests used in standard SSRF. A server's virtual network location is no longer a valid proxy for authorization. Zero trust principles must be rigorously applied to all backend-to-backend communication.